Okay, we're going to carry on with alkenes now. So let's start on this. Okay, so what exactly are alkenes? Alkenes are actually a homologous series of hydrocarbons. Okay, hydrocarbons, as we mentioned, it is the organic compounds with hydrogen and carbon only. Okay, but what's so special about alkene? They actually contain one or more carbon-carbon double bond. So how do they look? You'll actually see this. So this is the carbon-carbon double bond that we are talking about. Okay, so you'll see this double bond in the carbon in the middle. Okay, they are also considered unsaturated hydrocarbons. Okay, because they are containing carbon-carbon double covalent bonds. Okay, so just take note, the word unsaturated is actually linked to the idea that there's this carbon-carbon double bond. Okay, so as a start, let's take a look at this one over here. Okay, so let's start off with some of the simpler alkenes with the names and stuff. So ethene, okay, so ethene, so this is a 2-carbon alkene. So obviously the next one, what we're going to have is a 3-carbon alkene. So 3-carbon alkene, we know there is a meth is 1 carbon, but take note, there's no such thing as a 1-carbon alkene. Okay, no such thing as a 1-carbon alkene. Why? Because you need a carbon-carbon double bond. So if I need a carbon-carbon double bond, I can't possibly have 1 carbon and have a carbon-carbon double bond, right? Okay, so no such thing as a 1-carbon alkene. No such thing as a methene. If ever you say the word methene, this is rubbish. Okay, no such thing. So 3-carbon alkene, what exactly is a 3-carbon alkene? So we're going to have propene. Okay, prop-in. Okay, 3-carbon alkene. And of course 4-carbon will be butene. But in. Okay, so this is a 4-carbon alkene. So number of carbon, ethene, I got 2 carbons. Propene, I got 3 carbons. Butene, I got 4 carbons. What's the molecular formula? Okay, so take note of this, okay? The general formula for alkene, so the general formula is actually CnH2n. So to determine the molecular formula, okay, the molecular formula of my alkenes, I can use the general formula to determine. So in this case here, ethene, okay, 2 carbons. So I know that it is a C2H, 2 times 2. N is the number of carbon, okay, so N is the number of carbons. So this will tell me that my molecular formula is C2H4. This is the molecular formula. Hence, let's look at propene now. So I got C3H, 2 times 3, so it's C3H6. So this is the molecular formula, and the last one, I'm not going to do the calculation, just straight jumping into it, it's C4H8. Now, let's draw the structural formula where you have to draw the bonds. So take note, whenever you draw the structural formula, actually the first thing that you need to do is to draw the carbon chain. Draw carbon chain. Okay, so you draw the carbon chain. So the first thing, ethene, I got 2 carbons. Second step is actually to draw the functional group, if there is. So I'm going to draw the functional group. In this case here, the functional group for alkene is actually the C double bond. Okay, carbon-carbon double bond. So I'm going to insert the functional group there. Then the last step is to fill up all other, is to insert H. Okay, insert H to complete the bonding. What do I mean by that? Okay, it's because, you know, each carbon will have 4 bonds. So in this case here, this carbon on the left-hand side actually currently only have 2 bonds. So I need to draw another 2 more hydrogens. Okay, 2 more hydrogens. To make sure that I got 4 bonds on the left-hand side. On the right-hand side, same thing. You realize that this carbon on the right-hand side, I got 2 bonds already. And I need to draw 2 more hydrogens to complete it. So this is my ethene. Now let's look at propene now. So propene, first thing, draw carbon chain. I got 3 carbons. So I draw the carbon chain. Next, draw in the functional group. So I can draw a double bond here. Okay, some of you may question, Cher, can I draw the double bond over on the right hand side? Answer is yes, you can also. Okay, so it really depends. It doesn't matter as long as you have your functional group in. Next is to insert the H to complete the bonding. So one carbon on the left hand side over here, I already got 2 bonds, so I need to draw another 2 more H to complete the bonding. Carbon in the middle actually already has 3 bonds, so I just need to write 1 more hydrogen here. Last one, the carbon on the right hand side. Okay, 3 more hydrogens. So this is the formula for propene. Okay, this is full structural formula for propene. Last one, butene. So first thing, 4 carbon chain. Followed by, what I'm going to have is insert the functional group. So I'm going to have a double bond over here. Anyway, let me redraw this one nicer a little bit. Okay, followed by hydrogen. So same thing is to just insert H to complete the bonding. So let's draw it out nicely. Okay, so this is my butene. Now there's another butene that you could have drawn, which is that instead of the carbon-carbon double bond is over here between the first and second carbon, you could have drawn it in the second and third carbon. So let me draw it out for you in a different color, so you can actually do the comparison. So 1, 2, 3, 4. So 4 carbon, the carbon chain over there with a double bond in the second and third carbon. Once you've done this, then now you fill it up with H. So it will look slightly different. Okay, but eventually they are all still considered as butene because it's a 4 carbon alkene. Okay, do take note, ethene, propene, butene, all of these are actually very short chain alkenes. Okay, they're actually very short chain alkenes. Now, what I'm going to do is I'm going to switch over to the slides, okay, to just run through everything with you. Okay, so we are going to the physical properties of alkenes now. So do take note, alkenes, they are all gases. Now, please take note, when they say they, it's actually referring to the 3 that we have drawn just now. Ethene, your propene, and your butene. Okay? As the carbon chain actually increases, the melting boiling point will increase and they will actually become either liquids, and if the chain is long enough, it can even become a solid. Okay, but all this really will depend on how long the carbon chain is. So when we say they, actually referring to the 3 that we have drawn just now, which are ethene, propene, and butene. Okay, next we're gonna have is, okay, as with alkenes, the boiling point of alkene, as with alkane, the boiling point of alkene actually increases as the number of carbon atoms in the molecule increases. Okay? Or as the molecular size increases lah. So the boiling point, so let me use the highlighter. The boiling point of an alkene increases as the number of carbon atoms in the molecule increases, which actually implies that the molecular size increases. So 1, 2, sorry, let me draw this properly. Don't know why it's lagging, but yeah. Sorry, just on the lag. Okay, so let me go back to this. As with alkanes, okay, the boiling point of alkenes will actually increase. Okay, it will actually increase. Okay, when will it increase? The number of carbon atoms in the molecule increases. Okay, which means that the molecular size increases. So you will know that the boiling point increases when the molecule becomes bigger, the molecular size increases. So how do you actually know that the molecular size increases? Is really because the number of carbon increases. Okay, so that's with that statement over there. Next, for alkenes, there's a presence of C double bond C, but for alkanes, there's no C double bond C. So this is known as the functional group, okay, for your alkenes. Okay, for alkanes, actually there's no functional group. Every single thing is just a C single bond C and a C single bond H. Okay, chemical properties. Now when we're looking at chemical properties, we're looking at the reactions. Okay, reactions. RXN, reactions. So let's take a look at the reaction now. Okay, combustion. So combustion. Okay, so alkenes will actually produce more soot, okay, than alkanes. When we say soot, we're actually referring to the carbon. Okay, when they burn in air, because they have a relative higher percentage of carbon when alkanes with the same number of carbon atoms. Okay, this one, do take note of that. Okay, but however, if we have sufficient oxygen, we will always have complete combustion of alkenes. And what is the product? Whenever you have complete combustion, you're going to have carbon dioxide and water. Okay, so complete combustion is actually our reaction with oxygen. Okay, this is always going to give you carbon dioxide and water. When we say, mention at the top there, it produces more soot, generally when we say this, we say that there's a higher chance of it having incomplete combustion. Okay, so when the percentage of carbon increase, okay, it means that chance of incomplete combustion is higher. Write this properly again. Combustion is higher. Okay, so just take note of this. Okay. Now, next one, other than combustion reaction, alkenes actually undergo what we call the addition reactions. So what exactly is this addition reactions, and what's different from this compared to alkanes? Okay, you realize that I'll just keep drawing reference to alkanes because that's something we've learned before. So now, alkanes, if you realize that, yeah, sure, alkanes, I also know, sorry, let me write this again. Alkanes, okay, I know they got combustion, okay, because we have gone through that. Alkenes, also not so special, alkenes also has combustion. But what is the difference in the next part is really, alkanes undergo what we call substitution reaction, whereas alkene undergo what we call an addition reaction. Why is it so? It's really because alkene has this C double bond C. It is unsaturated, so that's why it can undergo addition reaction. So let's take a look. So the double bond in alkene can be broken, okay, to allow other molecules to add to the carbon atoms to form a single product. When we say it can be broken, we are not referring to both bonds breaking at the same time. No, we are referring to when we have the carbon-carbon double bond, we are breaking one of the bonds. Okay? So a single product is a saturated organic compound. So after the addition reaction, you will actually form a saturated. That means no more C double bond C. Okay? It will disappear. So other addition reactions, examples of addition reactions are actually hydrogenation, bromination, hydration, and addition polymerization. What exactly are these? Hydrogenation is to add, because it's all addition reaction. This one is to add hydrogen. So making sense of all these examples of all these terms definitely is important because it does help. Bromination obviously is to add what? Add bromine to the alkene. Hydration, the word hydrate tells you that it's already about adding water. And addition polymerization, we're going to learn this later on, is about adding itself, adding more of itself. More of itself. So just take note of this. We're going to carry on this later on. Next one. Okay, so addition of alkenes can be represented in a general equation. Okay, so you can see here the C double bond, XY, and things like this. So what exactly is happening here? Okay, I'm going to draw in this little corner. So we have the C double bond C. So yeah, let me erase this. C double bond C. Okay, when you have the X and Y coming in, so I have my X and my Y coming in. Okay, so take a look at this corner over here. When X and Y comes near this C double bond C, what exactly happens? You can imagine it being like this. Okay, when they come near, they're going to add it in. How exactly do they add in? The C double bond C will actually break. Okay, then you realize, sure, Now each of these carbon only have 3 bonds. They can form one more bond. This X and Y, the bond will break. Then they will attach themselves to each of the carbon. Okay, so I repeat again. So let me draw it again for you. This is your C double bond C. You got X and a Y. So when the X and the Y approaches the C double bond C, okay, one of the bonds in the double bond will break. The bond between the X and the Y will break. And then they will join in like this. So you really see that the X and the Y adds into the alkene. Okay, in the end what you're going to have is a saturated organic compound. So can you see this saturated now? Because why? All single bond, my double bond disappeared. Okay, this one initially is unsaturated. Okay, so yes, next slide. So let's look at the addition of hydrogen. Okay, so I'm going to add hydrogen in. So take note, this condition is important because in organic chem, this condition, yes, you must know, you must write it in when you have the reaction. So alkenes react hydrogen at 200 degrees Celsius using nickel catalyst. This is how you're going to write the equation itself. Ignore the blue line. Okay, you can see this is a copy paste, cut snip. So you must have this condition over here above the reaction arrow. Okay, so when I have hydrogen with my alkene, okay, so alkene, when I put hydrogen with it, the hydrogen is going to be added in. Okay, the hydrogen is going to be added in, and we're going to have our alkene. Okay, this is actually your alkene. How do I know? You look at this now. Okay, look at the bottom here. Initially, I got ethene. When I add hydrogen in, I actually get ethane. Can you see the alkene becomes the alkane? Okay, alkene becomes an alkane. So this is after your addition reaction. So take note, you can see once again, on the reaction arrow, this is actually the condition for the reaction. Okay, so it's very important for organic chemistry, you need to have the condition on top of the arrow. Okay, if there is the condition present. So how exactly does it look if I were to draw the reaction? You have a C double bond C. Okay. What I'll normally try to do is, you realize I'll actually try to rearrange the hydrogen bonded to the carbon, to the top and to the sides, so that I have a space at the bottom for my hydrogen atom. Let me see whether I can change the color pointer, the color, ink color, let's change to blue. Okay, now I got 2 hydrogens at the bottom. So what's going to happen here, okay, is that now I'm going to change the color again to something that is different. And let's change it to green. Okay, so at this stage when a hydrogen comes in, okay, what's going to happen? As I mentioned, one of the carbon double bond will actually break. The bond between the hydrogen will break, and they'll bond like this. So that's how you can get your ethane. So it's very important to be able to visualize. You must be able to feel. Okay, I use the word, you must be able to feel. Okay, how the reaction is actually taking place. Don't just purely memorize it. Because if you have a feel of how the reaction is taking place, you will be able to understand this whole reaction better. Okay, next, chemical properties of alkenes, addition of bromine. There's a video there, okay, so please go and watch the video, okay, to see how the color change actually occurs. But now this addition of bromine, so it's called bromination, that's another word for it. So if ethene is passed into an aqueous solution of bromine, because the word aqueous is there, so you will actually see the state is AQ. Okay, the reddish brown color of bromine disappears. Why is it so? Because bromine is gone. Let's take a look at the reaction itself. Okay, so I say again, okay, so let me change my ink color. I like red color. Okay, red color is good stuff. Good stuff, huh? Red color. Okay, so if ethene passes in the aqueous solution of bromine, do take note, the reddish brown color of bromine disappears. So how the reaction looks? So you got ethene, you got bromine. You realize, hey, how come this one? No condition. Yes, because this one at normal room temperature, without additional pressure, without any catalyst, it will just take place. So it's a very readily available. It's a reaction that takes place readily. Okay, so take note, aqueous bromine or bromine, we sometimes call it bromine water. Okay, is the reagent used to test for carbon-carbon double bond. Why? Because this is very, very visible. Okay, so how exactly does the reaction take place? I'm going to draw it out once again. Carbon-carbon. bromine comes in. So what's going to happen? One of the double bond will break. The bond between the between the bromine will break, and they'll join up. That's how you get. Do take note, look at the name over here. This is called 1,2-dibromoethane. So it is still a, after the reaction, you can see it still has the F there, ETH, so that means it's still 2 carbon. A and E tells you they're all single bond. Okay, there's no presence of double bond. Now, why is this considered 1,2-dibromo? The word dibromo means that there's 2 bromine, okay, that's attached. Now, what is this 1 and 2? The 1 and 2 tells you that they're attached across the first carbon and the second carbon. Okay, so it is a 1,2-dibromoethane because I got 2 bromine, one of them attached to the first carbon, one of them attached to the second carbon, and this is 2 carbon saturated organic compound. Okay, now I want to highlight the third point, the point mentioned here, because right, in actual fact, ethene is just a gas. Okay, it's a colorless gas. Okay, imagine you got a brown solution. So this bromine solution is actually a reddish brown solution. Okay, so yeah, with bromine, reddish brown solution. Okay, colorless gas passed into this reddish brown solution. What I'm going to have at the end of the day, this guy over here is actually a colorless liquid. So it's actually quite cool if you think about it, is that when I pass the gas through a reddish brown solution, it suddenly becomes colorless. And when will this react? It is when my aqueous bromine actually reacts with an alkene. And that is why we can actually use aqueous bromine to test for C double bond C. Okay, so this guy here can actually be used to distinguish. Okay, so this aqueous bromine can be used to test for C double bond C, which means that I can use it to distinguish alkene from the other homologous series. So take note of this. Okay, you're gonna see homologous series. Okay, so take note, you will see this coming out quite a fair bit here and there. So please take note of all of it. Okay, let's now continue with the next slide. Okay, what are the chemical properties of alkenes? What are the reactions? So we've got addition of hydrogen, addition of bromine. Now we're going to look at addition of steam to alkenes. So hydration, steam is actually your H2O, right? So it's addition of water. Okay, so take a look at this reaction here. So they produce this thing called alcohols. Alcohols means that they must actually have a functional group of OH. Later we'll see over there. Okay, conditions. Okay, do take note. This time around there's a conditions again coming up. So the temperature is 300 degrees Celsius. There's pressure involved here, 600 atmospheric pressure, 60 atmospheric pressure, sorry, and phosphoric acid, H3PO4. Okay, so you can see over here, once again on my arrow, you have all this over here. Okay, so you actually can write them on the same line, it's up to you. Okay, but take note, they are always at the arrow there. This actually tells you the condition of the reaction. So how exactly does this reaction work? So take a look. I have my alkene at the bottom over here. Water, think of it as there's a H and a OH. With the condition, it becomes like this. So let me draw for you to take a look at. So I got my C double bond C. So once again, let's have it over at the top. I want you to imagine the H and the OH as different stuff. Okay, so what do I mean by different stuff? That means don't see it as three. You group them together. So first one, maybe I'll write H over here. Okay, I want you to imagine the OH as combined together. So take a look at this now. Let me have a blue color. I want you to imagine the O and the H together. Okay, so just imagine H is one particle, OH is another particle. Okay, cluster the OH together. Then let's draw the bond. Okay, so this is actually how it looks initially. Okay, so ethene with steam. when the ethene and the steam comes together at 300 degrees Celsius, 60 atmospheric pressure with phosphoric acid, what you're going to have is the bonds breaking in between the H and the OH, okay, and the C double bond, C1 of the bonds will break and they will attach like this. I do take note, this line over here is connected to the O, not to the H, okay, because eventually this is how it looks. So I'm going to get an ethanol. So this is a 2-carbon alcohol. Whereas the functional group of this alcohol, okay, you actually have it over here. Okay, it's actually this. This is the functional group of the alcohol, the OH group. Okay, so you have 3 reactions now. Reactions with hydrogen. Okay, reaction with hydrogen. Now you have a reaction with bromine, and last one, reaction with steam. Okay, so yeah, let me change my pointer back to the pen. Okay, next. Oh no, okay. Oh no. Next slide, please. Okay, last one is addition polymerization. So this is when monomer units join together without losing any molecules or atoms. So when we talk about this monomer unit, okay, we are actually referring to the alkenes in this case here. Okay, these alkenes. Okay, they are like, like your building blocks. Okay, so I got many alkenes coming together and they'll form a long chain, a long chain. Okay, so alkene molecules, which are my monomers, so they are like the mono stands for single. Okay, mer stands for unit. So I got many single units coming together and they react to form a long molecule called a polymer. Polymer means many, poly means many, mer means unit. So many single units come together, they bond to form a long molecule which consists of many units. Okay, the condition that we have is actually high temperature, 200 degrees Celsius, high pressure, 1000 atmospheric pressure, and catalyst, depending on what is the monomer that you're using, what's the polymer you want to achieve, and that's where the temperature and the pressure will actually adjust accordingly. Okay, so this is an example of ethene. When you have the N over here, tells you that there's like many. Okay, so yeah, with the N over here, it tells you that there's many. Okay, many ethene come together, you put them together. The high temperature and pressure of the catalyst as the main condition, you're going to get what we call a polyethene. So take a look at the way how it's done. Okay, take a look at the way how we have written it. The polyethene. Okay, actually sometimes you can, without this bracket, I can just write polyethene. Okay, so what exactly happens? Okay, so a high pressure and temperature in the presence of catalyst, ethene undergoes additional polymerization to form a long chain molecule called a polyethene. So the ethene is called a monomer. The polyethene is called your polymer. Single unit, many units. Okay, widely used in plastic bags, bottles, films, or wrapping. So this is the plastic that we regularly use. Okay, now before we go into that, I just want to show you how the reaction looks. So ethene we have over here, so ethene. So this is a monomer. Okay, this is a monomer. Now for addition polymerization to occur, we need many monomers, right? So let's just draw a few more. I don't want to draw many, I just draw a few more. You realize that I will tend to arrange the hydrogens facing the top and the bottom. Okay, so you realize I will make sure that my hydrogens is facing the top and the bottom to make the sides of the carbon free. Okay, to make the sides of the carbon being more free. Now, so let's say I got these 4 monomers coming together. Of course, there are many more. Okay, so what exactly happens when this monomer comes together? The first thing that will happen is that, I want to make them bond, so you got a high temperature, high pressure, the catalyst. Okay, you actually break the C double bond C in the middle over here. All the C double bond C in the middle will actually be broken in the midst of all those conditions. So think of it as I got 2 hands holding each other. Okay, 2 hands initially holding each other, but now I break one of the hands away, and then they'll open up to the sides to combine. Okay, they'll open up to the sides to combine. Now, so I say, the bond not connected. Yeah, because I want to show you that when they open up, here you see these 2 bonds are linked to each other, right? So actually, they're connected. Okay, So yeah, let me redraw this for you. So actually when they open up, right, they actually bond to each other. When they open up, they actually bond to each other. When they open up, they actually bond to each other. Because you can't just open up and do no bonding, right? So let's redraw this again. So imagine, okay, let's reimagine it. So actually it's a very simple concept. All of this has the C double bond C, right? Okay, in the midst of the addition polymerization reaction, all the double bonds break and they will bond to the carbon beside them. So this carbon will bond to this carbon beside him. This carbon will bond to this carbon beside him. This carbon will bond to this carbon beside him. This carbon will bond to another carbon that's beside him. This carbon will bond to another carbon beside him. And you get what we call a long chain hydrocarbon. Now, but of course, we can't draw it like you know, many, like you don't draw like thousands of it, right? So what's a simple way we do it is, you realize that this whole thing here, okay, this guy is like the basic unit. Okay, it's like the basic unit, Okay, this guy here is like the basic unit, and we are like repeating it. Okay, so this basic unit that we are using it to repeat, we actually call them the repeating unit. Okay, just imagine it's like your primary school tessellation. You need a repeating unit, right? You need a basic unit that you're going to repeat. So the basic unit that's going to be repeated is actually this thing in the rectangle bracket. So I'm going to draw this, actually the repeating unit. But you do take note, you realize I got the two bonds at the side there. Okay, so this is my repeating unit. And then what is the formula of this whole polyethene? Okay, you actually draw your repeat. So the formula of the polymer, it's actually, first thing, you draw your repeating unit first. So repeating unit is like the very basic baseline. Once you have your formula, once you have the repeating unit, you draw a big bracket like this, and then put an N. So this is the formula of your polymer, because you know that your repeating unit repeat many times, N times, to get your full polymer. Okay, so this is your polyethene. So deduce the structural formula of a polymer given the monomer. First thing, write the structural formula of the monomer. Okay, like what you have seen here, like what I've described. Okay, what happens is that the carbon-carbon double bond actually breaks. Poof. Okay, open up the carbon-carbon double bond to form single bonds. Okay, each monomer forms a single bond with two other monomers. Eventually, they join to form the polymer. So you get a polyethene. Okay. Ta-da! So this is your polyethene, like what I've just described. Okay, if you have any questions, feel free to approach me. Okay, I can explain more to you if you need. But it's actually quite a relatively simple idea. So okay, feel it. Okay, feel how the bonds form. Repeating unit. Okay, I'll typically advocate this. Okay, and the structural formula, can you see this is actually, the inside is a repeating unit. You draw the big bracket with the N over here, you get the structural formula or the formula of the polymer. Okay, this is actually a condensed form. This is the condensed form. Okay, I need you to be able to see how this is actually linked to this. Can you see two hydrogen bonded to this carbon? Two hydrogen bonded to this carbon, just like this over here. Okay, so be able to see how the condensed form is linked to this big one. Because sometimes in the exams or sometimes you will see people writing this, okay, the condensed form. Okay, so let's go and try some questions on page 9. Okay, an addition polymer is added to carpet fabrics to reduce flammability. Part of the polymer chain is as shown. So this part of the polymer chain. Draw the full structural formula of the monomer used. So I want to draw the single unit. Okay, this is actually the many unit. So this is the polymer, the many units here. I want the monomer, and then you have been given the structure of a part of a part of the polymer chain and asked to draw a monomer. Identify repeating unit first of all, and then draw the structure of a monomer. Okay, so first thing, what is the repeating unit? So you look at this whole diagram here, ask yourself, what is the repeating unit? Which one is the one that you can stem to go and form your whole big chain? So realize this whole thing here, this is your repeating unit. Why? Because you can actually take this as a single repeating unit to go and produce this. Realize they're same to produce this. So you can actually take the one in purple to go and stem and stem and stem and stem. Stem, when I say stem means S-T-A-M-P-R. Just imagine like the stem is boom, 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 boom. Hey, you can produce many, many of it. So the first thing, I had to identify the repeating unit. Okay, before I even do the monomer, I need to identify the repeating unit. So the repeating unit looks like this. Chlorine at the top, chlorine at the bottom, H at the top, H at the bottom. So this is my repeating unit. Now, how exactly do I convert this into my monomer? Okay, the monomer will actually consist of the double bond because it's before the bonding occurs. So how exactly do I do it? Okay, you just need to imagine the two little hands at the side here comes back to the middle. So when it comes back to the middle, I'm going to draw the double bond. So the hand has actually combined back to draw the bond in the bottom over here. Okay, so this is the monomer. Okay, this is your monomer. You don't need to draw the rectangle bracket. I just want to show you that this is the monomer. Okay, so this is how you go about determining what is the monomer. It's actually from the polymer. You go and find out what's the repeating unit. And then from there, you can find out what's the monomer. So obviously, the reverse is also true lah. So you can actually, with the monomer, find what's the repeating unit. From the repeating unit, you can find your polymer. Okay, polymer. Woohoo! I love the multicolor. Okay, so this is how you can go about determining from polymer to monomer and so on and so forth. Okay, now let's continue with some fats and the oil. Okay, so we're going to look at fats and oil now. Okay, do take note. There's a difference when we say the word fats and we say the word oil. Okay, so fats, when we talk about it, we're actually referring to margarine and butter in general. Whereas when we talk about oil, we're looking at vegetable oils, which are corn oil and olive oil. Okay, they are actually similar in terms of chemical properties because they are like your organic compounds. Okay, but what's the difference between them is really more of a physical property difference. It's really about the melting point. Okay, so fats generally have higher melting point than oil. Okay, fats have higher melting point than oil, so they tend to be solid. Okay, so fats are typically solid at room temperature. Okay, because they are mainly saturated. So when we talk about saturated, it means generally no C double bond C. Okay, all are either your C single bond C or C single bond H. Whereas oil has a higher proportion of unsaturated fat molecule. Unsaturated, the word fat make it confusing. So unsaturated, there are generally higher proportion of unsaturation. Let me erase this. Higher proportion of unsaturation. Okay, so they are typically liquids. So you can see the difference really is the state that they're in at normal room temperature. Okay, so vegetable oils are large organic molecules. Long carbon chain in vegetable oil contains carbon-carbon double bond. Okay, as mentioned to you already. Okay, because they are unsaturated. So if they have many carbon-carbon double bond, we use the word polyunsaturated. So I think by now you understand poly means many. So we've got polyunsaturated oil. Okay, means it has many C double bond C. Okay, so there's the rest of the fat molecule, but you can see here the unsaturated, how many carbon double bond do you observe? 1, 2, sorry, maybe I shouldn't just highlight that. I should circle the carbon. 1, 2, 3, 4. Yeah. So can you see in this chain here there's 4, and there's still the rest of the fat molecule that is not inside here. Okay, there's still the rest of the maybe the rest of the molecule. Use the word fat lah. Oil, maybe use the word oil molecule lah. Okay, oil molecule. Let's just put the difference between fats and oil. Okay, we're talking about oil, talk about fats. Slightly different, the way how it's being mentioned. Okay, so we know that oil and fats are different because of the saturation. Okay, so the question is, can we convert oil into fats? Can we convert our regular vegetable oil into our margarine and butter. Okay, a lot of cooking, okay, baking, more of like baking products, actually we use butter. Okay, so can we use butter instead of our vegetable oil? Okay, can we make our oil into our butter? Answer is yes. Okay, so production of margarine. Okay, so we can do that. Realize margarine is made by reacting vegetable oil with hydrogen at 200 degrees Celsius in the presence of nickel catalyst. You think, this sound like very, very familiar. This 200 degrees Celsius nickel catalyst hydrogen. Oh, yes, correct. You identified it correct. This is actually the addition of hydrogen with my alkene. So we have picked this up previously. So because you realize that for alkene, if you do addition of hydrogen, it becomes alkane. So you are converting unsaturated into saturated. That's actually what you're doing when you're adding your hydrogen. So what you can see here, you can see the double bond present here. After you do your addition of hydrogen, tada! You got your saturated fat. All your carbon-carbon bond here, all your carbon-carbon double bond disappeared. Okay, and they actually form your carbon-carbon single bond. Okay, because the hydrogen is added in. Okay, break. Okay, so you can see that's how you can go about forming your saturated fats, huh? Okay, so let's do a little practice. Whoa, practice. When hydrocarbon X reacts with bromine, the product Y is formed. Okay, the product Y is formed. Deduce the number of carbon-carbon double bond present in one molecule of X. Okay, so this is the first part. Now, if you look at this here, or you look at this, react with bromine to form product Y. So initially it's a hydrocarbon, means that there's only carbon and hydrogen. Only these two only. So then you realize, how come got 4 bromine here? This is the trick here. So what you know is that, every time when I whenever you add bromine, you're actually adding Br2. But how come got 4 over here? What it means is that the bromine, I must have added 2 of this whole bromine, Br2. Okay, when it looks like this, it looks difficult, right? Because you look like, how come one bromine here, how is it exactly being added? So you can actually rearrange the position of bromine. So if you rearrange the position of bromine, put them all to the same side, it actually makes it a lot easier. So carbon. Okay, so this hydrogen and bromine are gonna rotate the thing. I'm gonna rotate these two together. So I'm gonna get hydrogen at bottom and left. At the top here is bromine. Carbon, hydrogen. At the top is bromine. Carbon. At the top is bromine. Hydrogen at the bottom. Carbon. That's carbon, hydrogen, bromine at the top. Now, with this, it's actually slightly easier now. Okay, this is after bonding. So before bonding, okay, I know that I must have added 2 bromine, right? So what I'm going to do is I'm going to group these 2 bromine together. So if I reverse the reaction, because remember I showed you how the whole mechanism might have worked, right? That means like how really the reaction occurs. Okay, you know that this bromine must have formed a single bond with this carbon. This bromine, okay, let me change a different color for you to see. Pointer, let's use green color. So you know that this bromine here will form a single bond with this carbon. This bromine will form a single bond with this carbon. This bromine will have a single bond with this carbon. This bromine will form a single bond with this carbon. So I want to reverse the reaction. I must break. Let's do step by step. Let's look at the bromine on the left hand side here. So this is the left bromine. These two are put on the left hand side. I'm going to break the bond. Then the bromine will form a single bond, right? Between these two bromine. And when the carbon to the bromine bond is broken, I must have formed a double bond here. Okay. Let's relook at it, but now we look at the right hand side here. So reverse the reaction. I'm going to break the bond between the carbon and the bromine. So ready step by step. I'm going to form the bond between the bromine. I'm going to form the bond between my carbon. Okay, so this is actually the initial stage where I have my 2 bromine molecules coming together to the alkene. Okay, and then they will add across the two carbons. Okay, the two carbons at the left hand side, the two carbons on the right hand side. So digits number of carbon-carbon double bond present. Actually, if you don't know how to reverse the reaction, you know that because I got two bromine here, so I need two carbon-carbon double bond. So therefore, answer for this is 2. Okay, draw the structural formula X and write equation for the reaction. So actually, you realize I've done it here already. So I'm just going to write the answer over here. Let me go back to my favorite red pen. Okay, let me go back to my favorite red color pen. Okay, so I'm going to have this C, double bond C, H, single bond, C, double bond C, H over here, H over here, H. I'm going to have my two bromines coming in. Okay, so two bromines coming in. Two bromines are. Okay. So this is my structural formula of X. So this is my X. What's happening here? I'm going to draw like that. So this is where I have my X over here reacting with two molecules of bromine. Okay, what I'm going to have is my molecule at the top over here. Okay, so my 4 carbons. I'm going to write my bromine all at the bottom now. So you realize it's quite flexible where you can place your bromine. Okay, at this particular stage over here. Okay, so this is actually how it looks. Some of you who say, how about I need to adjust this? Can I combine? Yes, you can. You can put 2. Okay, 2Br. Because it's an equation, right? So this is actually how it looks for part B. Part B is over here. Okay, part A is this. This is part A. Last one, part C, calculate the percentage composition by mass of bromine in Y. So how much bromine? So first thing, you have to find the percentage composition of mass of bromine. You must first, ask yourself, Y, what's the MR? So what's the MR of Y first? Okay, what's the MR of Y? Okay, so the MR of Y, what you have is actually there's 4 carbon. There is 6 hydrogen. So 1, 2, 3, 4, 5, 6. 6 hydrogen. Plus 4 bromine. Okay, if you look at the periodic table, the mass of carbon is 12. The mass of hydrogen is 1. The mass of bromine is actually 80. So you got 48 plus 6 plus 320. So you're going to get, this is 54. 54 plus 320, so it's 374. Okay, 374. So MR of Y is 374. How to find the percentage composition by mass of bromine? Okay, so we're going to find percentage of bromine in Y. So this will be 320 over 374 times 100. Okay, 320 over 374 times 100. Okay, let me press my calculator. So after pressing the calculator, you realize that the percentage by mass is actually 85. Let me double check again. 85.6. Okay, 3SF, 85.6%. So it is to 3SF. Okay, so take note of that. Okay, so this is the answer for this practice question. Okay, the last few parts already. We are nearing the end for alkenes. So the manufacturer of alkenes, manufacturing. Okay, so manufacturing of alkenes by cracking. So the thing is, alkenes are actually very useful. You can convert them to many different things. So how can we make them? Okay, first of course is your through your fractional distillation of your petroleum. Okay, of your petroleum. Okay, but the next thing is, if let's say there's a lot of other kinds of alkanes and stuff, you realize, I need to, do something to produce more alkenes. So actually what we can do is, we can do this process called cracking, okay, of your petroleum fractions, such as your naphtha and stuff, okay. So cracking is a process where large hydrocarbon molecules are broken down, so large hydrocarbons are broken down into smaller molecules, okay. So next example, hexane being broken down into a butane and an ethene. So this is actually how it will work out. You got C6H14. The carbon chain has 6 carbons. After going through cracking, okay, it will become a smaller chain. Now, because this one has, because this one actually requires a catalyst, the condition here. So in actual fact, it shouldn't have an arrow just like this. It will be C6H14. Okay, with the condition here. So I'm going to write 600 degrees Celsius, high temperature, with my aluminium Al2O3 and SiO2. So your condition should be on the arrow itself. And then after that, with the condition and the whole reaction here, you're going to get a C4H10 plus C2H4. Now you do take note, you can see C6, 4 plus 2, I got 6. H14, 10 plus 4, I must have 14. So the whole thing is actually a balance. You really just take the big chain and cut it up into smaller chains. Okay, smaller molecules. So long chain, generally, the long chain alkane or the longer chain alkane, you're going to have a mixture of alkenes plus a mixture of short chain alkanes or hydrogen. So you realize the alkane is going to give you alkene plus either alkane or hydrogen. Okay, so you can see longer chain alkane becoming a alkene plus an alkene. Okay, so take note of this because you may be required to understand all these little things. Okay, so cracking of liquid petroleum, let's take a look at it. So this is a simple setup. You can actually refer to the YouTube video to go and watch it. Okay, so you have a glass wool soaked in liquid petroleum. So you heat it up, it will convert into gas. The gas will go through our catalyst over here. So this is our catalyst. Okay, so we typically may not write aluminium oxide and silicon dioxide. We may just use the word broken porous pot. So you must know that this one is actually this two over here. So as it passes through, it undergoes catalytic cracking. Okay, and your mixture of your alkenes with either your alkanes and hydrogen will be contained inside over here. Okay, all inside here. Now cracking is very important because it produces these three substances. First thing, okay, actually it produces petrol. When I talk about petrol, we are referring to the second fraction. This is a second fraction. Sorry. Second fraction. Okay. Of your fractional distillation of your liquid petroleum. Of petroleum. Fractional distillation of petroleum. Okay? So there's a difference between petroleum and petrol. Don't go and confuse them. Okay, so the amount of petrol obtained from petroleum is actually insufficient to meet the demands in the world because petrol is used in cars. There's so many cars around the world, actually that's insufficient. So what they'll do is, because there are not a lot of places that need lubricating oil, diesel, also not many cars are really diesel cars. So what we will do is, we actually convert them into petrol by cracking. Okay, we'll convert these two into petrol by cracking. Okay, to meet the demands of petrol. So you realize that this is more of industrial consideration, like I now know how to do cracking. I want to crack these two fellas down into smaller chain, which is my petrol. Next thing, okay, hydrocarbons in petroleum are generally unreactive, so they are converted into alkenes, which are very reactive. Okay? You realize that alkenes, they actually undergo quite a fair bit of reactions. So you got addition of hydrogen, addition of bromine, addition of water, hydration, your addition polymerization. So actually alkenes have quite a fair bit of reaction going on just because they have this C double bond C. This C double bond C actually helps them to be able to react. And last one, okay, by cracking you can produce hydrogen as well. Okay, and you can actually use it to make ammonia in the Haber process. So we've actually gone through the Haber process where you got nitrogen plus your hydrogen, okay, in a reversible reaction to produce your ammonia. Okay, just a quick recap on this. Okay. Now kind of think of it, maybe you can do a quick recap, like really what's the condition. So you realize conditions are also introduced in the Haber process itself. So what are the conditions? First thing, okay, take note, Haber process, 450 degrees Celsius. Alright, that's the first condition you must remember. Second thing is actually is at 250 atm atmospheric pressure. And last one, there's a catalyst involved, is your finely divided ion. Okay, so actually the idea of condition has actually been introduced to you in the Haber process. Okay, but anyway, okay, back to this. Okay, when you crack your long chain alkane, you can get petrol, you can get alkene, you can get hydrogen. Hydrogen important for the reaction. So what actually happens is this C18H38 big chain alkane actually breaks down into an alkene. This is actually another alkene. Cool stuff. Okay, two alkenes. How do I know it's alkene? Because it follows the formula of CnH2n. And last one, I got hydrogen. So you can see how I can have multiple products. Okay, it's not just only two products at the same time. I can have multiple products as well. So take note of that. Cracking actually, you realize that it can produce more than just two products. Okay, isomerism in alkenes. So isomers, they are the different forms of the same thing. So same molecular formula, but different structural formula. Right? Same molecular formula, different structural formula. So these are called isomers. So typically, isomers have different melting and boiling point. The explanation is because our branch chain have different boiling points than the corresponding straight chain. Okay, so when you have branching, it tends to be a bit different because when you branch it, they tend to be more compact. Okay, the idea is they tend to be more compact and hence actually lower surface area. Once you have this lower surface area, right, the intermolecular force of attraction will actually be lesser. Okay, so you can see it goes back all the way to your bonding. Once the intermolecular forces of attraction is lesser, therefore my boiling point of the branch chain is actually less than the straight chain. Okay, so this is quite clear cut. Boiling point will definitely be lesser. Okay, so key idea. Okay, yes, they have different melting boiling points, so actually it's a different physical property lah. Okay, so isomers and alkenes. So if I got propene, I can actually have cyclopropane. Cyclo just means that there's a closed circle lah. Okay, when you see this cyclo here, actually it's a closed loop or a closed circle. Okay, so the first member alkene of cis ethene do not have isomers. Propene actually has two. Okay, so I say propene got one more, right? The carbon double bond can I form here? So some will say maybe if I just draw exact same pattern, exact same pattern. But instead of the carbon double bond form here, I form over here. This one like that can or not? Is this another isomer of propene? Answer is no lah. Okay, because you can actually take the molecule, you rotate it 1 by 180, you actually get the same. You actually get the same propene over here. So therefore, this is not considered an isomer of the previous one. Okay, so it's about the rotation. The other way is look at the number of carbons, but that one maybe I'll tell you all more in details in the subsequent times. Alright, butene has 4 isomers. Okay, you can't really see it, but I'm going to draw it out for you because all these are missing. So carbon, bond to hydrogen over here. Okay, double bond, carbon, single bond H, single bond C to 2H over here, bond to another carbon. Okay, I don't know why all this drawing got a missing thing. Maybe it's for me to draw on. Okay, next one. Okay, this second isomer. So this isomer actually has my double bond actually between my first and second carbon. Okay, maybe I should then use a different color to draw this. So the C double bond C is actually on the first and second carbon. So I'm going to use green color to show you first and second carbon. Okay, now let's go back to red color because I love drawing red. So next one, this one over here, I got H bonded to C, bonded to H, H, C bonded to H, double bond, bond to H, bond to C, then I got H, H, H over here. Oh, maybe I should just draw it to fit it here. Wait. Wait. So at least I get to fill it up. Okay, so this is my second isomer. This one here, the double bond is actually formed between your second and third carbon. So you can see second and third carbon, the double bond is there. So the position of the double bond actually is different. Okay, the third isomer is actually now a branch chain isomer. Okay, so it's a branch chain. So carbon over here, bond to a hydrogen, bond to a hydrogen, bond to a, so there's a, let's follow this. So CH2, double bond, C, single bond, CH, H, H. So my longest chain is actually 3 carbon. Then I'm going to branch out to a H over here, H. So you can see this is slightly different, okay, because my longest chain actually is 3 carbon. Alright, so this is another isomer, and the last one is a cycle. This is actually a cyclobutane, cyclobutane, because you can see these 4 carbons are in a closed loop. It's a circle. Okay, so you can only form a cyclo when it was alkene. Okay, because this idea of the closed loop actually is sort of replacing the double bond. Okay, yeah, you will learn more of this in your tertiary education. So it's actually quite fun. Okay, a lot of divergent thinking. Yes, divergent thinking. So, okay, these are your 4 isomers. Okay, draw isomers for pentene. Okay, I can draw a few for you. Actually, there's quite a few permutations you can draw. But of course, first thing you can draw is the cyclo one. Okay, the cyclo one is actually quite cool because it looks cooler. Okay, I'm gonna draw it like that. Okay, so 5 carbons in a ring. Okay, I'm gonna draw for you all a cyclo version. Okay, you actually condense this down. Okay, so instead of drawing all out, if you are not required, if you don't need to draw the full structural formula, you can actually do this. Okay, so instead of drawing all the bonds out, you can actually draw this. So you know that each of this is a CH2. Each of this is a CH2. Actually, your pentene, okay, another isomer could be a 4 carbon chain. So I start with a cyclo butane first. I draw another chain with a CH3. So you can count the number of carbons, you'll still get your if you count the number of carbons, you're still gonna get your C5H10. Same molecular formula, but different structure. Okay, of course, then someone asks, can I draw a cyclopropane? I mean, it's possible, right? So actually I can have a 3 carbon, like that, and followed by 1 carbon, like that. Okay, so you can actually draw like this, CH2, CH2, CH, CH2, CH3. And I say, actually this one I can draw another one. Yeah, you can draw another one. Okay, so you can see the possibility of your cyclo is actually quite cool one. There's a lot of possibilities that can have. Okay, hopefully you can understand what I'm drawing. All these are actually our cyclo. This is a cyclopropane with 2 carbons branching out. This is a cyclopropane with 1 carbon branching out from 2 of the carbons in the cycle. Okay, so all these are the cyclo products you can form. Pentene, let's just draw the longest 5 carbon chain. Okay, then I have my first double bond over here. Then this will be a CH2, CH, CH2, CH2, CH3. So this is my first isomer. So this double bond is formed between my first and my second carbon. I can also have another one. Okay, I draw my 5 carbon chain again. Now my double bond is formed between my second and my third carbon. Okay, second and my third carbon. So this one over here, okay, will actually be my second isomer. Now someone says, can I draw now 5 carbon chain again? Okay, but now I draw the double bond in my third and fourth carbon. Now, do take note, you draw between the third and fourth carbon, it's actually the same as this one over here. Why? You realize by counting 1, 2, 3, 4, 5, I can also reverse count from the right hand side, 1, 2, 3, 4, 5. So these double bonds actually form between the second and the third carbon. Okay, because I can flip the whole molecule 180, I can turn it 180 around, and you realize, it actually looks the same. Okay, so in terms of a straight chain, by adjusting the position of the double bond, there's actually only these two available. Next, from a 5 carbon long chain, I now go down to a 4 carbon chain. Okay, then after that I branch out. So maybe I branch out over here. Okay, so this is a 4 carbon longest chain, then 1 carbon down. I can have a double bond over here first. Okay, so CH2. I don't have this. So CH3, CH2, CH3. Okay, so this is a possibility now. And of course, you can go on and so forth. So, I just draw everything for you all. So you all can go and compare your answers of your divergent thinking. So next one, I'll have a C. I have 4 long chain again. My carbon branch out here. But now instead of my double bond being in between my first two, I draw it in the middle here. Okay, so this is CH3, CH2, CH over here, this is CH3. So this is a 4th permutation. Another one, actually still back to the same chain. Okay, C over here. Then now I'm going to put double bond over at the first one. So I say, isn't the double bond over on this, for your 5th one, the same as my 3rd one? Actually, no, it's really because of the branch chain. It makes a difference. Okay, it makes a difference. So anyway, back to this. So if I were to do this, the next possible compound would be this CH3, this is CH, this is CH3, this is CH, this is CH2. Okay. 5th one. Okay, man, this is very tiring, but okay, another one you can go. So other than my cyclo products, I actually still have some more. So you can, anyway, this part you can skip if you don't want to see every single thing. I don't want me to talk about every single thing. The last one will be my 3 carbon chain. Okay, if I branch out 2, it will be exactly my 3, 4, 5. So I'm going to branch one out, at the top and the bottom. So this, sorry, I haven't formed my double bond. Sorry, wait. Double bond C. Okay, now I have CH2. Can I do this? No, actually I realize I can't. I can't do this. Because why? Down here got 5 bonds. So I can't do this at all. So I can't have a chain that looks like this. Okay? So therefore, is it possible to form a 3 carbon chain? So actually it's quite impossible to form this because any one of these carbon form double bond, the middle become 5 bonds. So actually therefore there's no 3 carbon chain. So I think this is all the permutation you can form. Yeah. Okay, well of course you can let me know if I may have missed out any. So this is not really set in stone because to draw isomers tend to be a bit more of a divergent thinking of the various possibilities. Okay, so let's continue. Okay, we're going to go on to the last part. So we are done with alkenes. You can see alkenes is actually quite a big part because there's quite a lot of things to cover for alkenes. Okay, now we're going to go on to the 3rd homologous series, which is actually your alcohols. So we got our page 12 over here. So let's go through our page 12. So methanol. Okay, methanol over here. This is 1 carbon. So we have our 2 carbon over here. Ethanol. We have our 3 carbon over here, propanol. We have our 4 carbon here, which is our butanol. So you realize you always end with the OL over here. Okay. Molecular formula. So this is where it gets a little tricky over here. Okay. So to know the molecular formula, actually I'll suggest you can think of it as the general formula. Okay, this is actually a CN H2N plus 1 OH. Okay, CN H2N plus 1 OH. So the OH always there because it's our functional group. Then you got CN H2N plus 1. This is the chain that's bonded to the OH. So for methanol, C is 1. So C1 H 2 times 1 plus 1. Then OH. So you realize it's a CH3 OH. So same thing, okay, ethanol, I got C2 H 2 times 2 plus 1 OH. So this will be equals to a C2H5OH. Then if you were to continue, this will be a C3H7OH. This will be a C4H9OH. So this is the molecular formula. The structural formula is to draw it out, right? Okay, to draw it out. So realize there's a full structural formula and there's a structural formula. So this one is a more condensed form. So this one is actually the CH3 bonded to OH. Actually, if you ask me, I would reverse this because I know that my OH is bonded to my carbon. This one over here, how it looks, I have my CH3 bonded to a CH2 bonded to a OH. This one will be a CH3 at the side here, bonded. I shouldn't draw that. Let's make it simple for everybody lah. CH3 bonded to a CH2 bonded to a CH2 bonded to a OH. And the last one, you can see here is 4 carbon chain. So I got CH3 bonded to a CH2 bonded to another CH2 bonded to another CH2 bonded to another OH. Okay, so I think you can get the idea lah. It's a very long chain. Okay, so the full structural formula or the displayed formula over here. So you need to draw it all out. So when you say full structural formula, okay, we're actually referring to you must draw every single bond. So whenever you say full structural formula, you must display every single bond. Display all bonds. So I got C here, bonded to 3H. So actually we have been drawing the full structural formula for every single thing. This one over here, you can see it's a very long chain. So C, H, 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 C, H, H, O. Common mistake is you tend to draw the OH together, but you need to open it up. Okay, another one. Actually, I think the next box here is to draw the isomer, but never mind lah. I just draw the isomer, you can determine yourself lah. Okay, let's draw the next one. CH3, CH, H, H, CH, H, CH, H, and OH. Okay, so like this. Okay, last one. C, H, H, H. I think you have enough of me saying this, so I think I'll just be talking to you normally instead of saying the H, H, C, what, blah, 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 okay? Oh yes, I'm done drawing all of it. So you can see here, this is the overall stuff, okay, overall table that you need to draw for your alcohols. Okay, so alcohols are actually volatile liquids, okay? That's why you realize that in our hand sanitizer, you realize that when we put it on our hand, it tends to evaporate very quickly. Hand sanitizer actually contains alcohol in them. Okay? But when we talk about these alcohols here, they are volatile liquids, referring to your first four that we mentioned just now lah. Your methanol. Methanol. Your ethanol. I think you get the idea lah. Methanol all the way to your butanol lah, which was the 4 that we mentioned at the top just now. Okay, so alcohols are volatile liquid at room temperature and pressure. Molecular size increase, solubility of the alcohol decrease as well. As the molecular size increase, the boiling point also increase. Force of attraction. So you realize this idea of becoming bigger, boiling point will increase because the alcohol size increase. Force of attraction. This force of attraction we are looking here is your intermolecular force of attraction. I put FOA lah. So please don't forget the word intermolecular. Okay. So you can see the boiling point gradually increase. The solubility getting lousier and lousier. Okay, getting unable to dissolve, more and more insoluble. Okay. Yep. Okay, chemical properties. Yes, we are at the reaction. Chemistry is all about reaction. All the beam, beam, boom, boom. Okay, very good. So first thing, yes, just like all organic compounds, they undergo combustion. Okay, so if you burn in excess air, you produce carbon dioxide and water. The reaction is highly exothermic, where you have a nice flame and stuff. Okay, so this one can also be liquid lah. So depending on whether you dissolve this ethanol in water or whether you got pure ethanol. So pure or maybe dissolved in water. Okay, so it really depends. So this is actually ethanol. So read the question carefully. If they say pure ethanol, you should put it as a liquid. If you see that this is an ethanol dissolved ethanol solution, then it's aqueous. Okay, so take note of that. The word solution tells you yes, dissolved in water. Okay, you can see I think I'm a bit cranky here because the lecture has been going on for 1 hour 15 minutes here. I need to entertain myself. Okay, next, oxidation. So alcohol can be oxidized. Then you say oxidation. Redox? Yes, redox. So alcohol, what can you oxidize them into? So alcohols, you can actually convert them into carboxylic acid. So undergo oxidation. When you heat it with oxidizing agents such as acidified potassium manganate 7. This fella here, very distinct. It is your purple solution. It's a purple solution. Okay, if really it takes part in a reaction, okay, you know that when this guy here takes part in a reaction, so if it undergo my redox, you know that it's going to become colorless. So it's a very, very nice color change. So the MnO4 minus are reduced to manganese 2 plus. Okay, so the color change from purple to colorless. In the lab, we can actually do this. Okay. Okay, sorry, let me change this. This is out of the syllabus already. Let's continue the train of thought. Acidified potassium manganate 7. Okay, solution, which is your KMnO4. Okay, no more dichromate. Dichromate, remove our syllabus because it's toxic. Okay, cancerous or toxic. I can't remember which one is it. Right? Okay, yeah, but yep. Okay, because of the chromium. So take note of this. You can actually oxidize alcohols into carboxylic acid. Okay, so this is actually how you can see here. Let's change this to your potassium manganate 7. Okay, please go and change all this. Don't go and write dichromate. In your exam, don't use dichromate. Okay, so you mix your ethanol with your potassium manganate 7. You heat it. Actually, also to you don't just put that. Actually, you let it react, heating it a bit. Actually, you'll heat it up. You can see here, because you're not required to know the exact reaction in terms of the chemicals, what's happening. So you realize we put a 2 bracket O here. So understand that this is really about the gain of 2 oxygen. Okay, and that's what you get. This is your ethanoic acid plus water. Okay, so in this reaction, acidified potassium manganate 7. Okay, actually acts as oxidizing agent, and ethanol acts as a reducing agent. Okay, take note, this guy in red here, the potassium, this highlighted in red. Okay, acidified potassium manganate 7 is an oxidizing agent. For redox to occur, the other fella, in this case your ethanol, should be the opposite, which is the reducing agent. Okay. Okay, just ignore this. Ignore this whole statement here. I'm going to write the statement at the top over here. So please write the manganate 7 ions. Okay, this guy here, purple. Okay, it's going to convert, it's going to be reduced to your manganate. To your manganese ion. Okay, manganese ion, which is your Mn2+. Okay, so take note, the color change. And this guy here is colorless. Colorless. Let me be consistent. This guy is MnO4 minus. This guy is Mn2+. This guy here is colorless. Okay, so at least you also know that what exactly is what causes a color and stuff like this. Okay, so this is the reaction of alcohol, how I can convert to carboxylic acid. Now I can also prepare ethanol in the lab. Okay, in the lab, ethanol can be made in 2 ways. First is obviously what you have learned, addition of steam to ethene. Okay, so but the next one is actually the fermentation of glucose. Now this one, please go and recap. Whenever you see such thing, you must ask yourself, hey, what's the condition? What exactly is happening? What's the reaction? Okay, so use this opportunity to go and recap. Okay, you can pause here, go and recap a bit before you come back. Okay, so ethanol can prepare with addition of steam. Ethanol can also be prepared using the fermentation of glucose. We're going to look at the glucose one here. Okay, sorry, this one, let's go through this one again. So phosphoric acid, 300 degrees Celsius, 60 atm high pressure. reaction fast and produces ethanol quickly. So this is actually good stuff. Okay, this is actually quite good stuff because it is fast. Okay, so this is what we have gone through previously, so just take note of it. Yeah, I'm not going to go into too much details, we have gone through it. Now, what I want to go through more is the fermentation of glucose. Okay, glucose is your, I think those who do bio, you know lah, C6H12O6. Okay, your sugar. So glucose solution is mixed with yeast. Yeast is important reagent. Okay, it's kept at 37 degrees Celsius. I don't know why there's so much spacing here, so please reduce the spacing. In the absence of, so you can see there's actually three things you must take note of. What is added with it, the yeast, what's the temperature, and there's one thing you must not have in the absence of oxygen. Okay, and what happens is that the yeast will actually break down the sugar into ethanol and carbon dioxide. So two products here. Later we'll see the equation. Okay. Of course, you know that carbon dioxide forms by precipitate lime water. That one will be a no-brainer. So you can see over here, look at the way how the reaction. Sugar, solution. That's why it's AQ, solution. Big arrow over here. You write yeast and 37 degrees Celsius. Actually, if you ask me, I will also write absence of oxygen. That's why you realize it's a sealed container. It's a sealed container here. And then we put lime water here, so air cannot go in. At the same time, we can test for the carbon dioxide that's coming out. So actually, this thing here got two purposes. One is to what we call airlock. Airlock the reaction vessel. Okay, airlock the reaction vessel. So air cannot go in. Okay, why you don't want air to go in? Because you want to have it as the absence of oxygen. Second function of this lime water over here, obviously, is to test the CO2 that's evolved. Okay, that has been produced. That's produced. Don't use the word evolved. Okay, that's produced. Okay, so there's two functions of the lime water over there. Really is to airlock. Okay, so air cannot go in, but can come out. Okay, take note, but can come out. Okay, next to test the CO2 that's being produced. Okay, because if you know that CO2 is being produced, you know that, yeah, my reaction is happening, alcohol is being formed. Okay, so this is how you can draw it. Okay, sometimes you may be asked to draw it, okay, and describe what actually happens. Okay, so it's impossible to make pure ethanol by fermentation. Why? Because yeast is killed. Okay, this one you must think, no, yeast is killed. Okay, when the mixture contains more than 15%. So the max you can get from this whole thing is a 15% ethanol, which is quite good, right? Your beer is typically about 5% or 3-point-something%. If you look at some of the wine, tend to be about 10 to 12%. 15% is quite good stuff, right? Isn't it? Okay, I mean, I'm not telling you make this at home, so take note of it. Okay, pure ethanol can be obtained from dilute solution of ethanol by fractional distillation. So in a sense, if once I got my 15% ethanol, okay, I can let it undergo fractional distillation to obtain my 100% ethanol. So you can see being a chemist is really cool stuff. Okay, if you know all this reaction, you can actually produce all of these little things at home. Okay, so this is the end for alcohol. I'm not going to go through any more because it has been 1 hour 23 minutes for my side. I'm going to speed it up a little bit, okay, on my end. Actually, you all on YouTube can speed it up on your own end. Then, yeah, let's see whatever you need to see, fill up whatever you need to fill up. Okay, so for the fermentation of glucose, you must be able to describe and know some of these little things like 15% ethanol, okay, absence of oxygen, why is that absence of oxygen, okay, and stuff like this. Okay, so just take note of all this little stuff. Okay, so that's all from me. I'm not going to go into carboxylic acid because they're not tested for your end of year. We'll go through it after, not tested for your mid-year. We're going to go through it after your mid-exam. Okay, so that's all. Bye, everybody. Bye.